So good morning, and thank you for a very good presentation. It's a foundation for what I'm going to talk about today. Telecom at the Crossroads. My name is Hakan Djuphammar, Head of Technology in Business Unit Cloud and IP in Ericsson. And I will also later bring up on stage Mr. Brian Ahern from Intel to help me with parts of this presentation. So what crossroads are we talking about? I would like to use this curve or graph to talk about that crossroad. This graph is used in many cases to illustrate the major technology shifts that has happened in the society during the past 100+ years. It has an installation phase where you bring in new technology to solve an existing problem. Once you've done that, you realize that with this new technology, you can do new things. So we are basically at this cross point now in the telecom networks. As an example, when the electrical engine replaced the steam engine, that was in the installation phase, very few predicted the electrical toothbrush in the deployment phase. So this is a little bit what I'm talking about. And this change is fueled by three things: mobility, broadband, and cloud. And the presentation today will cover three areas. One is the transformation of the networks, the fact that we bring in Internet of Things into the networks, and that we are getting into industrialization of clouds. Clouds is becoming more of a commodity and a broader scale deployment. On the transformation of networks, even though this is a mainly fixed forum, I will start with radio. And that is just to put things in a context, because there's a lot of hype around 5G. And let me just give a big picture of how we view the concept of 5G. The history of radio evolution has been 2G, 3G, 4G, and then the natural step would, of course, be 5G, but it's not that simple, actually. When we go into 5G, there are different flavors of 5G. We have license-assisted access, LAA, which is already available, where you add access on unlicensed spectrum controlled from the licensed spectrum. We have LTE narrowband, which is a dedicated standard for machine-to-machine type communication, which has improved coverage, 20 dB better link budget, and a lot lower energy consumption. Due to longer duty cycles, you can have battery lifetime of 10 years on small devices. And then we finally also have the NX, the 5G radio access, which is extremely high speeds, low latency, 200 megahertz bandwidth. That is the big picture of the radio evolution into 5G. If we then look at the core network piece, the big shift has already happened. It was when we went from circuit switch to packet switched. And that happened already when we went from 3G to 4G. So in the core network, we now see a tremendous amount of things happening just because we shifted from circuit switch to packet switch. All the buzzwords you can think of is now showing up on the core network side based on this transition. And when we start to talk about 5G in this industry context, it's basically all this. So we're referring to 5G networks, 5G this, 5G that. It's this family of things happening in the telecom networks. If we then look at the core network again, what are the major shifts there? There are two major shifts that are profound. And that is the fact that we get IP on all the different layers in the network. And secondly, we introduce the concept of virtualization in the network. So starting with IP on all layers, in the existing networks, we have PSTN, XDSL, 2G, 3G, circuit switch type of technologies. And we're going to a world where all the accesses are packet-based and IP. So in the bottom, we have 4G, 5G, Wi-Fi, fiber. That is the access and transport layer. Then everything on top starts to migrate to IP as well. And that is a big shift happening. Things like SS7 signaling system changing to diameter signaling system. That means that operators suddenly now becomes part of an ecosystem which is completely different. Diameter signaling is used in the banking industry. The operators can start to do authentication of completely different use cases than they could do with SS7. The interconnect between operators change. It goes from the old ISAP circuit switched voice-only interconnect to an IP interconnect where you can basically interconnect on anything. Of course, you can interconnect on communication services with video calling and all these things, but you can also interconnect on cloud pipes, where I get the connection from a cloud user in one operator network to a cloud provider connected in another operator network. So the interconnect becomes versatile. Other effects is that when you go to packet-based access, you get the multi-access behavior. The terminal can choose different accesses and just roam between those. Wi-Fi calling is a typical example of that. Wi-Fi calling is a tremendous momentum in the industry right now, just because it solves two big problems for operators. Indoor coverage, everybody has Wi-Fi at home, and roaming charges. You can use the terminal in a roaming case with a local tariff. That is the multi-access. Then you also have multi-device. So you're not anymore confined to your actual phone. Your subscription can also be used on your iPad or tablet or PC, and you can just shift the session between those different devices. Those solutions are already available today. So this means that there's a lot of evolution happening on top of the access which has now gone IP. Roaming changes dramatically. Today, all service execution is done in the visited network. When you go to IP-based call control, you will backcall all your call control to the home network, and you will bring all your local services when you roam. That's a completely new paradigm in telecom. So that's the IP on all layers. Virtualization then, basically two parts. Virtualization of hardware. We don't have the monolithic nodes in the telecom network anymore. We have a data center infrastructure, and we put the virtual network functions as software blocks on top of that infrastructure. Then we also have network virtualization enabled by SDN technology. So today's autonomous IP networks, where each node is autonomous and talks routing protocols and self-healing networks, that's very good, but when you start to configure VPNs and all these things in the network, it becomes quite difficult to manage over time. And if you want an efficient network where you can utilize layer 1, layer 2, layer 3 capabilities in the most efficient way, you have to lift out the control from the nodes and actually do centralized management. And that's, with SDN, we get network virtualization with one physical infrastructure where you can create logical networks in that layer. So going back on what's the consequence on IP on all layers, it says consumer communication plus and business communication plus. That's just a given. Once you have done the transition to IP-based call control, there is no reason why you should stay with narrowband voice and SMS. It's so easy to add the new service capabilities that are available in the OTT services. And we see a lot of examples of that in the industry happening. The evolution going through messaging, sharing during calls, setting up conference calls easily. I talked about Wi-Fi calling, multi-device. And at the end, of course, naturally, every conference room in the world will have a screen which you can connect to any other conference room in the world, or any home, or to any conference room. That is just where we're going, just because we have now done the transition, and now we can start up the curve of deployment. Going back to the virtualization layer, there's one more thing we can do, because when we virtualize, we also introduce a lot of flexibility in the networks. So starting with hardware virtualization, where you disconnect the application from the hardware, and you add SDN capabilities to manage connectivity or virtual connections in the network. If you combine those two, you can start to build distributed clouds, where you put your network function on different topology places in the network, which can enable completely new use cases, which you couldn't do before. Now you can put the entire core network on a cruise ship, just by virtualizing. If you then have these three things and put management and orchestration on top of it, we get something we call network slicing. And network slicing is basically the possibility to configure one physical infrastructure to be used by many different tenants with different characteristics. And we just heard that in the previous presentation when we talked about MVNOs. That's a use case where you put a slice for an MVNO. Other use cases could be public safety, national security usage of the mobile networks instead of a separate Tetra network on the side. We see all those movements happening in the industry. So from a business point of view then, that means we have one physical infrastructure, one network with compute storage, transport, that can be configured to fulfill different needs for different use cases. So we can create slices that have certain characteristics and functionality. Within that slice, you can split it up on different tenants. So each tenant, a company, enterprise, view it as their own network, as all the devices are connected on their internal LAN, basically, with characteristics that they have subscribed to and paid for. That leads us into the next topic, which is adding Internet of Things to the operator space or the operator business. In order to do this efficiently, we have to scale and industrialize. And we have to have a foundation first, which is the connectivity needs to be optimized for this type of communication, and that I already talked about. You will have LTE narrowband taking care of that. Then we have to have platforms that makes it easy to onboard these billions of devices. It's a completely different thing to provision a power meter than to provision a smartphone. Because when you provision a user, a subscriber with a smartphone, you have to set all these parameters. Should you have voicemail? Should you have this? What invoicing every third month or every second month, whatever? When you provision 1 million power meters, it's the same profile, and you don't have to deal with all these things. You have to have a completely different system to provision these types of devices. And Ericsson's value proposition in this is the Ericsson Device Connection Platform, which basically does this in a cloud outside the operator network. So the machine interfaces the enterprises directly through a portal, and the operator just agrees the cost between the enterprise and the operator, and then all the provisioning and onboarding is done on the device connection platform and management. And on top of that platform, then you can start to build the different applications. The device connection platform also provides global connectivity, by the way, through roaming agreements. So if you're a car manufacturer, you can put in a SIM card, and it doesn't matter where that car is sold or shows up, it will always have connectivity on a global scale. On top of that, you can then build all types of different applications, of course. And here is a lot of development happening using analytics to do intelligent conclusions and optimize business processes and so forth. We have another thing also that is happening, and that is that you don't go directly, or that you don't really have a 3GPP, or a cellular connection in the device. Because there are other access technologies that might be more applicable to the use case, where you have a lot of small devices that are in a pretty small distance from each other. And then you can use capillary networks, which means that the device talks Zigbee or Wi-Fi or any other short-range connectivity to a gateway, and then the gateway is connected to the cellular system. And those example of such a capillary network is what we have just deployed in Germany for wineries, where they have sensors measuring humidity, precipitation, temperature, sun hours, and logging all those data to get a perfect view of when it's time to actually harvest the grapes, or if it's necessary to add extra water into the system to make it better. And even though this is maybe not so obvious to hack these things, security is a very important aspect. So you don't want to have fraud into the system here. So what we have developed is a solution that builds on the SIM card authentication mechanisms. Now I'm back to diameter signaling that I talked about earlier. You use the SIM card in the gateway to actually set up an encrypted tunnel all the way from the device into the business process at the enterprise that is using those sensors. So this makes it possible to just deploy this anywhere in the world and get the fully, due to the global roaming agreements, put the gateway anywhere in the world, and it connects to devices that are connected over Zigbee or Wi-Fi, and you get a full encrypted tunnel all the way back to the back-end system that you are using to control your devices anywhere in the world. Beautiful solution. We just made a press release of this yesterday. In that gateway, there is a platform built by Intel. So that's one area where we cooperate with Intel. But there are many more areas where we cooperate with Intel. And I'll let Mr. Brian Ahern start to talk a little bit about that. Please welcome Brian.
Fantastic use case. Can you imagine all the other use cases that are out there? Use cases with remote sensors, secure data aggregation, hybrid cloud infrastructure, and a secure communications infrastructure in between. This is a great segue and a great backdrop to what I'm going to talk about for the next few minutes. Intel and Ericsson have a rich history of innovation in data networking, and our current relationship can be summarized in these three pillars. We're working together on performance optimization of the data plane using Intel Data Plane Development Kit and associated Intel technologies. We're collaborating in open source projects such as ODL and some work we're doing on service function chaining. And we're also working together on cloud and data center, specifically with Intel rack scale architecture and some joint go-to-market activities and technology alignment. Collaborating on open source projects is fundamental to moving SDN and NFV forward. Ericsson and Intel are working together on OpenStack, as an example. We're working on enhanced platform awareness to deliver the underlying infrastructure to ensure that we have the capability of executing and running the high-performance workloads that telecom network virtual functions require. There are many other projects that we're working on together, and we expect that to continue. Intel is also aggregating those open source contributions and providing the Intel Open Networking Platform. The ONP reference platform is an on-ramp, if you like, a fast start to NFV deployment. We truly value our relationship with Ericsson. It's a relationship that continues to go deeper and stronger. We're especially proud of our collaboration on data center and cloud. It's really exciting to see Ericsson apply all that history and expertise and know-how from telecoms in these new domains. Since Mobile World Congress earlier this year and the launch of the Ericsson HDS 8000, our collaboration has gone from strength to strength, with technology alignment, joint go-to-market activities, and engineer-to-engineer relationships. It's fantastic to see our teams collaborating, combining their know-how to deliver these innovative solutions to the market. Intel has a long history of innovation in the data center. We are delighted that Ericsson chose Intel rack scale architecture for their HDS 8000 platform. Pooling, disaggregating, compute, network, and storage resources, to deliver hyperscale cloud computing to service providers. We are delighted with the partnership, and we expect it to continue. And now, I'd like to hand back to Hakan, and he will outline how he has taken the Intel rack-scale architecture and brought forward this wonderful world-class HDS 8000 solution to the market. Thank you.
Okay, thank you, Brian. Yeah, as you've noticed, we're into our third piece here, which is the cloud industrialization. And we have used the rack-scale architecture to build something that is a little bit unique in the industry, but others are following. So what we're doing is that we are making the hardware software defined. So in the data center, you need different types of resources. You need CPUs, of course, memory and storage, networking and accelerators for different purposes. And different workloads requires proportionally different amounts of these elements which you have underlying in the data center. And if you just put out servers with the same characteristics there, you will not optimize the utilization of the different elements in each server. So what you can do with the HDS architecture is actually to software define pools of hardware that has different proportions of these elements depending on what the workload is needing. On top of that, the operator can then run the different types of clouds, which we normally refer to as the telecom cloud, for all the telecom real-time mission-critical applications. The IT cloud, where they run the more back-office type of systems, billing and things like that. And commercial cloud, which is the cloud that they operate to offer infrastructure as a service or software as a service to enterprises or consumers. So these three clouds can then be optimized depending on how you configure the underlying hardware. And just a note as well, as Brian already said, when it comes to standardization and industrialization of the cloud execution environment, OPNFV is what we're using as the vehicle to align the industry around this. So the actual product, HDS 8000, has three things in it. Disaggregated hardware, CPU, RAM, NICs, and disks, which you can lifecycle management completely independent of each other. And you can configure and add things on these four different areas as you like. And the reason you can do this is because we have a full optical interconnect. So it's light speed between those elements, so you don't have to think about where you have it. You just configure that much memory, that much storage, that much CPU, put it in a block. This is a physical entity, but it's actually virtual. To run this and to operate and monitor, we have the HDS Command Center, which actually shows the utilization and predicts that you need in 3 weeks this much more memory or whatever. So it's a full command center that can handle both the HDS piece, but also the legacy service that you have installed there to optimize the entire hardware pool that you are utilizing. Okay, so to wrap up, we had the three different areas. And if we start with the top one, virtualized and software-defined all-IP future. That's where the networks are going. It's pretty obvious. IoT acceleration. We have the things required to do that. We have the new optimized radio access. We have the platforms in place to provision and manage these devices efficiently. And hyperscale cloud, we have the tools to do that as well. And as a final pitch, I would like to mention that we will demonstrate as a proof point on the upper piece, virtualized and software-defined all-IP future. We're demystifying the thing with IMS, which is said to be extremely complex and big and cumbersome to manage. We put a full IMS system into a one-unit rack-scale box, and we will run a live Wi-Fi calling demo, which also has a local breakout. 10:30, just next to the Ericsson booth, you can see that demo happening. Okay, that was all. Do we have any questions, or how do we proceed?